Hey everybody, how's it going? Thanks for coming to the webinar. My name is Jordan. I'm here with Formlabs, Education Development Specialist. Got a lot to go through, so we'll try and get through it all. If you guys want, there's going to be a question and answer period near the end of the talk, so if you'd like, you can have an opportunity to ask us some questions. So this talk is going to focus on injection molding and 3D printing, but we're going to talk about some other molding types as well. We'll discuss how 3D printing can augment mold design and production, and we'll talk about the basics of mold design and demonstrate some CAD techniques that you guys can use for building your own molds. For those that are curious, this is a Bronze Age mold that was used to make spear tips several thousand years ago, so I just thought that was kind of neat. So these are all the processes that 3D printing can, the mold making processes that 3D printing can be applied to. Molds are typically used to cut down production time for multiple copies of a part. They're used for materials that are not easily shaped. And in the past, molds have been used to produce prototypes, but lately, 3D printing has obviously kind of supplanted that. That being said, not all materials can be used by a 3D printer, so there's something to be said for molding prototypes for, making molds for prototypes and short production runs. So what we're going to be focusing on are these three processes here, because we have seen 3D printing used for them, and we're going to go over them in a little bit more detail and then talk about how you can make your own 3D printed molds. So let's start with injection molding. This was first patented by a guy named John Wesley Hyatt in 1872. It was used to make collars, stays, buttons, and combs out of celluloid. The next two big developments were in 1946 and 1956. In 1946, the reciprocating screw that you can see in the bottom diagram was invented, and then in 1956, it was improved upon, and that improvement allowed injection machines to reach modern levels of efficiency and quality. So on the bottom right over here, you can see one of the very first injection molding machines. This was used by Lego, whereas on the top, you can see a modern industrial level machine. So the process, this is how it works. It's explained in the little graphic on the left, but basically you have little pellets of plastic that are fed in through a hopper. They go into a barrel, a heated barrel, with this reciprocating screw. The motion of the screw drives the pellets forward. As they get closer to the heater, they melt, and eventually the screw pushes it into the mold cavity. You can see that those little arrows here with the movable platen, I think it's pronounced, but basically you have all of this plastic being injected under pressure, and then the platen kind of clamps down to hold against that pressure, and it's not atypical to see pressures within 68 to 200 tons worth of clamping force. So when we developed our white paper, you guys can check it out online. We used a Galam model B100, and Dave Galam is actually on the call today. He's going to help answer some questions. But from Galam Incorporated, it's a similar process to injection molding, where you can actually see the original patent that Hyatt put in 1972. It works like a big needle. It's kind of the same way the B100 works. You fill up a plate or a little cup called the pot with plastic material. That material is heated, and then it's injected by pulling down a lever which shoves it into the mold. Again, we did a bunch of testing on this. I'll share some of the results of that during this presentation, but if you guys get a chance, I really recommend checking out the white paper online. Just Google Formlabs injection molding white paper and you'll find it. The next major process is casting. So this has been around, for thousands of years. The frog thing on the left is actually the oldest known casted part. It's made out of copper, and it's 3,200 years old. Actually, it's from the year 3,200 BC, so it's over 5,000 years old. The basis of casting is you have a hollow mold made from a master, so that master could be hand sculpted or 3D printed. Then you kind of surround it in the casting material, and then you pour in your mold, or your plastic or your metal or what have you. So some common casting materials that are used are sand, clay, concrete, epoxy, plaster, and silicone. In fact, if you guys are interested, BJB has made a great video, BJB Industries, on using a Form 2 to produce a silicone mold. So if you guys want to follow that bit.ly link, you can find it there. Another application for this is our castable resin. So we have a lot of jewelry makers that make small rings and then cast them in molten metal. Our support page The link's there, but you can just go to formlabs.com/support. You can find out like kind of the process of how that's used. It's a very useful process. It's very easy to use. And again, this is one of the easiest processes to get like real metal parts out of your casting. So the last process I'd like to talk about is thermoforming or vacuum forming. They're slightly different. It's first originally developed in the 1940s to produce aircraft canopies that didn't have any blemishes and army relief maps. So you could have a little scale model of the hill you're supposed to assault or what have you. The way this works, thermoforming is the first process that was developed. The way it works is you have two halves of a mold and a heated sheet of plastic. You press the sheet of plastic between the two mold halves and you come out with a part. Vacuum forming uses only one half of the mold, and it uses suction or vacuum to pull the plastic down over the part or the mold. It's very easy to use. The machines are very cheap. You can build them yourself if you'd like. On the left here side of the screen, you can actually see a razor case that was produced from a 3D printed mold using our high temperature material. The high temperature mold is on the left, and the final case is on the right. So typically when you're making molds in today's industry, there's two main methods. The first was CNC, and the second is silicone. CNC stands for computer numeric control. Basically, you have a mill that's guided by a computer that cuts away the part. These are really high precision. They're very, very durable. They're made for mass production. You kind of need these if you go out and buy any injection molded part today. It's made on a CNC machine. The downside to them is they're very expensive. They're not really great for prototyping because they're hard to work with. So a lot of people turn to silicone casting, which you can see on the right. So silicone casting is very cheap. It's great for kind of like one-off projects. I'll go over like how many pulls you can get out of them in a second. But they're very forgiving. Even if you have undercuts where one half of the mold can't be pulled out, so one half of the part can't be pulled out of the mold, you can kind of flex a silicone mold so that you can like kind of wrench the part out. The downside is it requires a lot of upfront time investment to make the mold, and you do need a master part. So whether that's 3D printed or hand sculpted, you're going to need that before you get started. So when you're thinking of how 3D printing, like which process you should choose, this is kind of how it breaks down, where silicone casting on the far left in terms of durability and cost, and then it kind of rising to CNC machining, and 3D printing is kind of right there in the middle. Silicone casting, you're looking at maybe getting 50 parts or less. 3D printing, you're looking at 150 to 600, and then of course CNC machining, you're looking at several thousand parts. So that's kind of a good breakdown for why you'd use this. Now, in terms of when you'd use this, generally 3D printing is good at prototyping individual parts in specific materials, whereas mold machines are great at a huge range of materials and making lots and lots of parts. So by combining the two of them, you can kind of get the best of both worlds. So for example, entrepreneurs, let's say you're on Kickstarter, you want to release your product to the testing, kind of validate it in the market. You can produce maybe 100 to 1,000 parts using this process, send it out to your customers, get real-world feedback, and then change and iterate on your design. Teachers, you can use this to teach your students how to do molding very inexpensively. And mold designers, you can prototype your molds before actually paying the money up front to go do a CNC mold. I'd also like to throw out for mold designers, there's a benefit here where you could offer a lower cost alternative to short run production for your customers. So like let's say they come in with 150 parts, rather than saying like doing like 3 silicone casts or spending the money to make a CNC machine, you could just 3D print one and you could have it all done on that single mold. Finally, as a product designer, you can prototype and use plastics, and you can actually prototype looks like and works like models at the same time. So you can make those short production runs, make it look exactly like the final part, use the same materials as the final part, and then give it out to maybe 1,000 customers and see what they think. So it's a really great tool for all of that. So in general, if you're looking to make copies of a part cheaply and easily, this is going to be cheaper and easier than using any of the other techniques. So 3D printing is going to be cheaper than CNC machining. It's going to be possibly easier than doing silicone molding. If you guys are listening live, I'd love to hear some of the ways that you've used 3D printing and molding, and I'm going to go over those in the questions and answers period later. But please feel free to send us any information on that. So in terms of use cases, the first one I have here is 3D Brooklyn. They're a small design service bureau in Brooklyn, New York. Great guys. I've worked with them on this project here where they kind of showed off their process. So what they're doing is they're using 3D printed thermoforming to make soaps, candles, and candies for clients in the realm of like around 500 to 1,000 parts. So they took some pictures for us to show their process. They'll 3D print a mold. In this case, it was a mold printed on the Form 2. And then they put it in a vacuum forming machine all the way on the left. They pull a piece of plastic down over it. In the middle, you can see them actually pouring the candle wax into it. And on the far right, you have the final product. In larger production runs, they'll actually do several mold pulls. So they'll have like maybe 10 of these that they'll all be pouring candle wax into at a single time. And that'll help speed them production. But yeah, I'd really recommend if you guys want to learn more about this or maybe have some design services that you need done, check out 3dbrooklyn.com. Next up is right-hand robotics. This is a great example of this using 3D printed molds in production. What they do is they make robotic fingers and grippers for the scientific community. So what they did was they 3D printed molds. They 3D printed these plastic parts that go inside the molds. They put them all together, and then they inject room temperature vulcanizing rubber into the mold, casts it, and then they pull the part out. And they actually send that to the customer. So this is a great example of like real world using molds, and I'm going to talk about them a little bit later when I get into digital direct manufacturing at the end of the talk. The last one here is, oh, there's not a last one. I actually got one little surprise for you guys, but the Shirley Technique, this was Shirley Anderson lost the lower half of his face to cancer. So at the Indiana University, they worked with him to develop a new prosthesis that would kind of let him live a normal life. So the process that they developed was they 3D scanned his face, then they used a sculpting application called ZBrush to sculpt a new, lower face essentially. And then they took that and 3D printed molds for it on their Form 2s, and they cast it in silicone. The end result ended up being a lot more comfortable, a lot more realistic than any previous process that they've tried before. So it's again another example of using 3D printed molds in the real world. This is the surprise here. Dave Galam just sent me this a couple days ago. He was trying to make a metal mold using 3D printing. So he casted it using Moldmax 60 by Smooth On. He poured in Zamak metal, which is an alloy that has a relatively low melting point of about 500 degrees. Then he kind of took out the cast, machined it off the top so it was perfectly flat, and then he casted the parts. Now you can see, it's not the best detail, but this is something he was just doing in his spare time to explore the concept. I find this personally really exciting because, it opens up the possibility with refinement that 3D printed molds could actually be used in end production injection molding machines. So we've talked a lot about, molds in general. Let's talk about how to design molds and how to design 3D printed molds in particular. The first thing you have to think about is the mold forces. So we're going to be talking here mostly about injection molding and transfer molding. A little bit with casting, but casting really doesn't have that many forces. The first thing you want to be aware of is the pressurized heated mold flow. So you have a enclosed chamber where you're shoving a lot of very hot plastic into that chamber at a relatively high pressure. So if you have any very thin features that are oriented perpendicular to the mold flow direction, so the direction would be that orange arrow, the mold flow could weaken them by either pushing them over or just outright breaking them and snapping them off. So any small features like that, any small protrusions, you want to make sure they're parallel with the direction of the mold flow. Outgassing, this is something that I didn't even consider, but basically as the mold flow displaces the air within your mold, that air gets more and more compacted. As it gets more and more compacted, it gets hotter and hotter. So if you don't vent that air out, you'll either end up with burns on your plastic part or your mold, or you'll end up with bubbles in your part. So it's very critical to remember to include air vents. Differential cooling and heating, this is especially important in 3D printed molds because they don't transfer heat very well. They don't cool down very quickly. So you want to make sure that your mold heats evenly throughout the process. Otherwise, you could end up with warpage, and that could damage your mold or even make it completely unusable. The next slide shows two last little bits here. Again, this is mostly for transfer molding and injection molding. Clamping force kind of applies to casting, but basically for both of them, your parts are going to shrink during cooling. So that's with casting and injection molding. What this means is, A, you might want to oversize your part slightly. It's kind of an experimental thing. And two, you're going to want to add drafts to your faces. What's a draft? We'll talk about that a little bit later. Just keep in mind that you want to add draft and you want to maybe oversize your part. In terms of clamping force, when you have an injection molding machine or transfer molding machine especially, you have to put force on it to keep it closed against the pressure of the incoming plastic. So you want to make sure your mold is strong enough to withstand that. Now, the thing here is that with 3D printed molds, there's definitely a ceiling in terms of maximum pressure and maximum temperature. It's kind of an experimental one. Depends on what you're making and like how thick it is. But just keep it in mind that your parts have to be strong enough. So maybe add some extra material or add some metal reinforcement. With casting, there's a little bit of clamping force because you do have to kind of tie it tight, but really it's almost negligible in terms of the part itself. When it comes to thermoforming though, there's only three like forces that the part undergoes, and really only the one that you have to worry about is heat. So heat is from the plastic itself, so we would recommend using something like a high temperature resin or a high temperature capable material, otherwise you could end up melting your mold. The other two pressures, if you're using thermoforming, you're going to have a pressure from the reverse mold face closing down. Using vacuum forming, not so much, but with both of them, you will have some pressure of the plastic being applied to the form. Now again, it's really about the heat. You really want to make sure to use high temperature capable material. So these are the parts of a mold here. I'm going to kind of just explain what each of these things mean, kind of point out the important bits. So first of all, this is an industrial injection mold. So a lot of the stuff you might not have in your, if you're tinkering at home. But you have two support plates that are on either side. Those are what clamp the mold together. The mold itself is comprised of the mold cavity, which is the negative, and the mold core, which is the positive. You can see here there's this ejector box. That contains these ejector pins, which push up and push the part off once it's done molding. Over here on the right, we have a locating ring, so that helps the nozzle kind of get guided into the sprue bushing. The sprue is the melt of the plastic that's going from the nozzle down to the part, so it kind of carries that down there. And then the runners take that melt and they distribute it to all the parts within the mold. So we have a part here, and then it's connected to the sprue by two runners, and then those two runners are connected to the sprue. The ejector plate, I'll show you in a second what all of that means, but the ejector plate is what holds the ejector pins, and those again push the part away. So if you're kind of wondering what the heck I'm talking about, I've got this little animation here that I put together that shows how everything goes together. So you can see the sprue bushing and the sprue washer come apart. So the support plate, and then right there, I'm going to pause it and go back for a quick second. You can see as the part gets pushed away by these ejector pins, it would fall off into a basket, and then the ejector pins would retract back down. This ejector bar is what pushes the ejector plate, and then there's a second piece, this ejector retainer plate, and that just helps guide the pins into the mold core. So when you have it all together, you have your injection mold. So it's quite a lot of parts for what might seem like a relatively simple process. So next up, designing your part and your mold. So there's a couple things you can do here. The first is you want to make sure to draft your surfaces. So you want to make sure that any surfaces that are parallel with the direction of the mold, you want to make sure they're angled in slightly. And the reason for that is if you don't do it, the friction caused by these surfaces will make your part very difficult or almost impossible to remove. So by adding a slight angle, you're reducing that friction because as soon as you pull it away, you have air kind of in between the two parts, the part and the mold. So just make sure to add draft. What you're looking at as an injection molding machine, you're looking at maybe a minimum of 1/2 degree, whereas thermoforming, you're looking at a minimum of maybe 3 degrees of draft. Filleting edges is important not only to make your part look better and make it more predictable, but also for improving the lifetime of your mold. So if you keep injecting and you have like tight corners, as you pull the part away, it's going to slowly degrade that area of your mold, and it'll degrade your mold very quickly in sharp corners. So by filleting them, you increase the lifetime of your mold, and you make your parts more predictable. When it comes to choosing a parting line, I used to work as an industrial designer. It was very critical for some of our pieces to make sure that the parting line was in a non-visible area. A parting line is where two halves of the mold come together. You want to make sure that that's either in a visually, you want to make sure it's in a spot where it's not going to be an issue. If visual aesthetics are a big important thing for your part, then you want to make sure to hide that as best you can. Obviously, you want to add vents to the mold. We talked about that a little bit earlier. You're looking at about maybe zero point 0.1 to zero point 0.2 millimeters tall in terms of your vents. You might even go a little bit smaller. It's really kind of a trial and error thing. With undercuts, you want to make sure basically that, so for instance, this orange little L shape here, I can't pull that out of the mold because there's part of the mold blocking it. So I'd either have to move the mold line or I'd have to redesign the part. So that's something else you want to be aware of. Finally, on this slide, you want to be aware of witness marks. So a witness mark is a runner mark, or sorry, where a runner touches the part. That's called a gate. It's a gate mark or an ejector pin mark or a vent mark, anything like that. It's where some part of the mold leaves a blemish on the part. And some of them are unavoidable, so you just have to either sand them down or you have to make sure they're in a hidden spot. If you'd like to see a witness mark, find some plastic pieces and then turn them over on their backs, and you'll often find little circles that are like kind of indented into the part, and those are ejector pin marks. Some other things you can do is you want to plan and test your injection cycles. There's a free calculator on improveyourinjectionmolding.com. Basically, you're saying like, okay, inject for 30 seconds, cool for 1 minute, do the next part, and this can help you optimize what you're doing, essentially. You want to be careful of warpage due to uneven cooling and heating. We already talked about that a little bit. Big one here is maintaining constant wall thickness. So plastic cools, and when it cools, it shrinks. And when it shrinks, it can kind of create surface blemishes on top of your part. So you want to make sure that to avoid that, your part cools at the same rate. So that's why you want to maintain a constant wall thickness. I really recommend at the bottom of the slide, there's two links. There's protolabs.com, the design cube, and then protolabs.com, the demo mold. The design cube shows you design rules for virtually every sort of plastic feature you can imagine, and shows you what happens if you don't do it correctly. So it's a great resource. And then the demo mold is just kind of like, it shows you how an injection mold goes together. And they're both free, and I really recommend checking them out. They're a great resource for designers. So again, it's on Proto Labs. Finally, on this slide, you can reinforce your 3D printed molds with metal bars. So if you're worried about maybe the mold crushing under pressure, you can try that, and you might have some success. When it comes to 3D printing a mold and designing it in particular for that, one thing you should be aware of is engraved and embossed details. Those should be exaggerated slightly, at least a millimeter. The molding process, you're always going to lose a little bit of detail, so when you're printing, you might want to bump up some of your detail a little bit more. Split plane surfaces, so basically where the mold halves come together, you want to try and get those, you can sand those down to kind of increase the tightness of the bond between the two when they're clamped. Any gaps will allow plastic to leak through, and that's called flash, and you'd have to trim that off later. So if you're having issues with that, try sanding those split planes. If you're using an aluminum mold frame, so like let's say when we were doing our testing with Galam's injection molder, we put our 3D printed molds inside aluminum frames, and those aluminum frames helped kind of distribute the force so it wasn't all on the part. But because of that, you want to add a little bit of extra material on the back of the part. So because when the molds come together, when the mold frames come together, your part might sit slightly below that upper lip, and you want to make sure you have a good seal. So when you bring them together, the part will compress slightly, and then it'll take up that extra material, and be sure to have a good fit. Finally here, you want to make sure that your parts are oriented so the supports are on the back side, or alternatively, you want to print them directly on the build platform. Big thing here is just it's saving you finishing time. If you do it the other way, you'll end up having to get in there into your tiny mold nooks and crannies and sand them down, and nobody wants that. So if you're doing thermoforming, there's not a ton of tips for this. It's actually very simple, again, very easy process to get into. You want to, if you're having issues with the part being pulled down, you want to add holes that go through the part that allow the vacuum. So technically, this isn't thermoforming tips; these are vacuum forming tips. You want to allow the vacuum to travel up through, get the air in between your mold and your plastic. So if you kind of suck that down, you can suck that down by adding some extra extra holes through your part. Adding holes in concave areas and then around fine details is actually very critical. So the left one you may or may not have to do. The right one you probably do have to do. It allows you to pull plastic down in those concave areas, and it's really important that you do that essentially. Otherwise, they might not show up at all. If you're having issues with fine details, again, try adding some holes around them. The next thing with thermoforming is you can add some material to the bottom of your mold to allow for a clean cut. So what do I mean by that? Basically, if you have, let's say, this half circle here, if you don't add any material to the bottom, the injection, when you pull down the vacuum form, it's going to cause this little bow out right there. And as you can see, the part goes to the bottom, so this essentially the bottom, like say, centimeter on this image is useless because you have this little bowed out area. But if you add a little bit of extra, say an extra centimeter to the bottom of the part, it goes straight down and that bow out is moved downwards. So you can just slice it right off at the bottom of the part and you have a perfectly finished part. So just something to keep in mind when you're designing for thermoforming. So in terms of the overall process, this is kind of the steps. Step one, design, print, put in the injection molding, injection, and you have your final part. Excuse me. If you'd like to use a standard aluminum frame, you can get those from an injection molding manufacturer. They're very common. You can have them custom machined by some other agencies. They're very it's not super expensive. I think for like maybe 4x4 it might be under $300. You want to be careful when you're using a 3D printed mold. High pressure and high clamping forces can and will probably break the mold, so you want to reduce those. You can, of course, sand and polish the parts if you want. 3D printed molds are especially good for thermosets. So if you don't know, there's thermoplastics, which are plastics that have to be melted to be injected, and then there's thermosets, which they get mixed and then they get injected and then they harden. So with thermoplastics, you want to make sure your mold can stand up to the heat and pressure. With thermosets, you just inject them, and then you just have to make sure that during the thermosetting process, it doesn't give off too much heat. Otherwise, just use a high-temperature resin. So here's some molding errors. We actually got 2 of these images from one of our users, plasticlabs.wordpress.com. I'd really recommend giving this guy a shot, giving this guy's website a visit. He's got some great material and stuff. This one over here is 2 little Lego figure Uzis that he was molding. It's pretty cool. But you can see that he had some issues with flash. So again, flash is just where the mold parts, they don't come together quite right. So the little bit of plastic leaks out, and you get this little bit that needs to be trimmed off. So you can fix that by either sanding down your mold, reducing the pressure and temperature of the injection, or maybe even clamping it a little bit tighter or something like that. Mold damage, in this case, it's from the hot nozzle of his injection molding machine touching the 3D printed part. Can't stand up to that level of temperature. Notice that he is using gray though, so I'm not sure what he was using, but he might have better luck with high temp. In general though, you want to use an aluminum frame. That'll that'll keep that from happening. With air burn right below it, so again, that's improper venting. It's basically the air has gotten so compressed and so hot that it's burned the part or the mold. He can fix this either by increasing the size or increasing the amount of air vents. He can also try decreasing the pressure that he's pushing it in, so it gives air more time to get out of the way. But those are some things that you could do if you find that. Over here on the right, finally, we have melt fronts. So basically, this is where if you have 2 flows of plastic, they meet, and it creates this stitched line where they join. It's a visual blemish, and sometimes it can actually be a mechanical issue as well. So if you want to fix that, just increase the pressure, increase the temperature, and maybe even make your runners a little bit bigger, just to try and push as much plastic into the mold as possible. If you guys want to learn more about common molding errors, let's say you start doing this yourself and you run into problems, bit.ly/fimtechmolding at the bottom of the screen. Check it out. They've got a huge list of mold errors and stuff you can do to fix them. So give them a shot. Actually, I think I used one of these or both of these from their website. So finally, as we get into material considerations, we're looking at this case. BJB has put together a great quick start guide, so you can follow it there. It tells you some stuff like Does it need to be fire resistant? Is clarity a requirement, etc. BJB, for those who don't know, they're BJB Enterprises. They make a wide variety of casting and mold making products. Again, they made that awesome Form 2 video on making a silicone mold using the Form 2. But yeah, just go Google. If you don't follow the Quick Start, just search BJB Quick Start Guide or BJB Quick Start Injection Molding, and it'll come up. So this is a list of materials that we tried with our printer. So this is, you can see it over here on the left. Our initial white paper, we only tried it with LDPE. It's slightly lower temperature at 163 degrees Celsius. Worked fine with our clear resin. We didn't notice any noticeable degradation of the mold itself. But once we started getting to the higher melting point temperatures, we had to start using our high temp. And it, as you can see, it performed admirably. We've got these are all little USB enclosures. You can see what they all came out like. One thing that's not on here is urethane. We got that tested by one of our partners, and that also worked pretty well. So it's a good example of some, like all the material variety that you can get out of these 3D printed molds. All right, so I'm going to jump into modeling a mold now. Just show you guys my process really quickly for how you could go about this. In case you're wondering, I'm using Fusion 360. So I made my part. This is the basic, part, right? It's nothing fancy. But the first thing I did was I shelled it, and the reason for that is because this thickness of the plastic, this level of thickness, the plastic in the middle would probably cool at such a slow rate that I would end up getting probably a sink mark on one of these sides. So as the outer plastic cools, it'll cool faster than the inner plastic. So the inner plastic is going to start to cool and pull that now cooled outer plastic inwards. So you get this kind of big divot on the inside. So you want to make sure your parts have a relatively thin wall thickness. You want to avoid big, huge chunks of plastic if you can. So the next thing I did was I added draft. So you can see with that, there's an analysis. You can go to inspect draft analysis. I've already set one up. Oops, let me turn off the section view. So you can see here green means that it has more than 3 degrees of draft. So the mold direction is going vertically. So there's more than 3 degrees of draft on this one. There's no issue. Orange means that it's exactly 3 degrees of draft. And then blue on the opposite side means it's all draftable. It's all okay. So I'm going to hide that, and I'm going to go to the next step. I'm going to add fillets. So I added fillets all the way around. This is not just obviously for making your part look good, it's also making it more easily moldable. You want to make sure you have fillets in your parts. And then I created a mold. So the way I created the mold is I just created a square that goes around it, 10 millimeters off on either side. And I just created an extrusion that's a separate body. And then I just subtracted my original part from the new one. So if I go to analysis again, you can see in my section view, oh, let me just make a new section view. Section analysis. There we go. So you can see this is my mold. So that's what's going to be made. So the next thing I did is I chose a parting line. So for this part, I chose the bottom of the part. So I drew just a straight line across. You can see it right here. The reason for that is because it's easiest for this sort of part because it has a flat bottom with no fillets. Let me get to the right view. Because it has a flat bottom with no fillets, that's a great place to put a parting line because it's not going to leave a visible seam on your part. And then I also, if you add a parting line on a fillet, so like say, right about here, right there, when you put two mold halves together, there's always going to be a little misalignment. So you want to be careful to make sure not to put a parting line on a fillet, because if you do, it'll separate, it'll be more obvious where the misalignment occurred. So by putting it on the bottom away from any fillets, it's less obvious if that should happen. So then I just split the parts and I'll have a top. So I'll show you, here's the core. Oops, I also combined it properly, so there we go. So this is the core, and then this is the cavity. So now I have two halves of my mold. And then next I created an injection point or a runner. It's kind of a combination runner and sprue because it goes straight from the injection port. Now you'll notice this is two things. One, it's only on one half of the mold, and two, it's shaped like a trapezoid. So the reason I did that is just to make it a little bit easier. In general, you want to have your mold, your injection port be on both sides of the mold. The reason for that is if I added an injection port all the way up here, there's no way for me to remove that little sprue once the part comes out of the plastic because it would be completely embedded. It would be an undercut. So by adding this trapezoid down here, I've allowed it to be removable. So like you can see, if I do this, you can see I still have the sprue. I could still access it. But at the same time, I'm also not cutting into this one just because the mold flow is going to be a little bit more difficult. There's a lot of different resources online for designs on how to design your own parts or design gates and runners and stuff like that. Just Google around. You can find a ton of useful information. The next thing I added was the air vents in the back. Two critical things here. One is they're very short. They're only 0.2 millimeters tall, and they're also parallel with the direction of the mold front. So as the flow goes through the part, it's going to push air straight back out of the mold. The next thing I did was I added a small gate. So the reason I didn't bring this sprue all the way to the part was because it's going to leave a very large blemish. So I kind of shrank it down and added a smaller gate that actually touched the part. And then finally, I filleted it. So the reason you fillet the top of this trapezoidal thing is because you want it to the mold to flow in there smoothly. And then again, for the same reason, I filleted the top where it connects to the smaller gate because again, I want the flow to go smoothly through the part and smoothly through the sprue and then down into the gate and into the part. So that's the basics of the mold design. You can see, I'll just show you again the final product. So this is the core. Here's the part itself that's over top of that. And then there's the cavity right here. So you can see how it all goes together. With the runners, with air vents, you also kind of want to only put them on one side. You don't really need to put them on both sides. So sprues and gates and stuff like that, they go on both sides. Runners really only stick to one side. And you can think of them kind of like flash on purpose. You want them just tall enough to let air out, but not tall enough to let a lot of plastic out.